Hi everyone, this is Mr. Bowman, and we are going to kick off section 6.3 with a video about the topic we are covering, which is parametric equations. And simply put, parametric equations are sets of equations that define x and y in terms of a third variable called a parameter. So let's write that down. Sets of equations that define x and y in terms of a third variable the parameter. Very often, as you will see, we use the third variable t, and we use that because often we use the third variable to represent time. And it's rather nice because we can take equations like you see in this first example, which represents projectile motion, and we can break those down to represent the x position or horizontal position of an object and the vertical position of an object. Before we get to something that complicated, though, I want to start out with a simpler example where we are going to represent the position of a boat traveling on Lake Michigan over time, and we are using x and y to represent the coordinates of that boat and t to represent time in hours. So to get some idea of how this boat is moving, we are going to make a table of values with t, x, and y. And since t is time in hours, we're going to start out at time 0, and we're going to make it easy and go in 1 hour increments. So let's plug those values for t into the equations for x and y and see what we get. At time 0, x is -8 and y is 0. At time 1, x is -2 and y is 2. At time 2, x is 4 and y is 4. And at time 3, or 3 hours, x is 10 and y is 6. So to get a visual of what that looks like, we're going to plot these points on an xy coordinate system to see what sort of movement this boat has. 1, 2, 3, 4, 5, 6, 7, 8. So at time 0, the boat's at -8, 0. At time 1, the boat is at -2, +2. At time 2, the boat is at 4, 4. And at, got that point in the wrong place, 4, 4. And at time 3, the boat is at 10, 6. So about right there. And if you were to connect these points, you would see that it appears the boat is moving in a linear fashion. Well, one of the things we often like to do is to eliminate the parameter and write the relationship between the two variables x and y without t in the equation. So what we do is we pick one of the equations and solve for t, usually the easier one. So in this example, I would pick the y equation and solve for t, and if you solve this equation for t, you get t is equal to y divided by 2. And then you would substitute that into the other equation, so x is equal to -8 plus 6 times y divided by 2, and you have eliminated the parameter. We're going to go a little bit further and put this into a form that we would recognize, so slope-intercept form would be useful here. So add 8 to both sides. X plus 8 is equal to 3y, and then we're going to divide both sides by 3, so we have 1/3 x plus 8/3 is equal to y, and we have our equation in slope-intercept form, and it seems reasonable that our line is the line with a slope of 1/3 and a y-intercept of 8/3. The next example is very similar, except we're also asked to name the type of graph. So again, pick one of the two equations and solve for t. So if I were to take the y equation and solve for t, I would have y minus 2 is equal to the opposite of t. Multiply both sides by -1 and get t is equal to the opposite of y plus 2. Then substitute that into the equation for x. So x is equal to 1 minus 2 times the opposite of y plus 2. And simplify. 1 plus 2y minus 4. So we've got x plus 3 is equal to 2y. And we can see that's a linear equation. Let's put it into slope-intercept form by dividing both sides by 2 and get y is equal to 1/2 x plus 3/2. So line. There are some situations where it's not quite as simple to eliminate the parameter, like in problem number 2, but I would always give the same advice. If you are solving for t, pick the equation that is easiest to solve for t. So the x equation, x minus 2 is equal to t. Substitute that into the y equation, 5 plus 10 times x minus 2 minus x minus 2 quantity squared. We're going to simplify this, so 5 plus 10x minus 20 minus the quantity x squared minus 4x plus 4. Combine like terms, so we have an opposite of x squared plus 10x plus 4x plus 14x plus 5 minus 20 minus 4, so a minus 19. And we have a parabola. The next thing we want to do is investigate what happens when we put limits on the parameter. So in this example, t has to be greater than or equal to -2 and less than 5. So what we'd like to do is to figure out the relationship between x and y by eliminating the parameter. So this is a pretty simple one to do. We have solved for t already in the y equation, so x is equal to 3 plus 6y. And you can see that that's a linear equation, and we're not going to go any further right now. But what we're going to do is we're going to take a look at a short table of values where we use the end points for t. So -2, +5, and we're going to plug in that into the xy equations and see what we get. So when t is equal to -2, plug that in for x, you're going to have -9 and -2, and plug 5 in for x, and you are going to have 33 for x, and you are going to have 5 for y. So what that tells me is that at time t equal -2, the x-coordinate is -9, the y-coordinate is -2, and at time 5, the x-coordinate is 33, so I'm just going to put that way over here, 33, and the y-coordinate is 5. So -9, -2. And now we know that what we have is a line segment, because we know we have a linear equation connecting those 2 points. If we had no restrictions on t, then we would not have a line segment, we would have the entire line. There are some situations when it comes to eliminating the parameter that solving for t in one of the equations and substituting it into the other equation just doesn't make sense. It doesn't help us a lot. And this is an example of that. If you were to try and solve one of these equations for t, like the x equation, you would have the following. You'd have x over 2 is equal to, x over 2 is equal to sine of t, and therefore inverse sine of x over 2 would be equal to t, which then we would try and substitute into the y equation, and we would have y is equal to 2 cosine of inverse sine of x over 2, which gets really complicated, and so we're not going to do that. We're actually going to use a trick here. And the trick is the following. It turns out that there's a relationship between the sine and the cosine such that the sine squared of t plus the cosine squared of t is equal to 1. And we can actually prove this by using the Pythagorean theorem. It's actually pretty simple to do, but for right now, you should just accept that as a fact. So we're going to use that to help us eliminate the parameter. So in this case, what we're actually going to do, instead of solving for t, is we're going to square x, we're going to square y, and we're going to add them together. So we'll square both sides of both equations and add them together. So x squared is going to be 4 sine squared t. Y squared is going to be 4 cosine squared t. And we can factor the 4 out and get sine squared t plus cosine squared t. And we get x squared plus y squared is equal to 4, because sine squared plus cosine squared is equal to 1. And if you don't recognize that, that is a circle, or the equation of a circle, with radius equal to 2 and a center at the origin. So that's it for now with parametric equations. We are going to do much, much more using them to model situations for us and solve situations for us. We just wanted to give you some exposure to what parametric equations are so that when we start applying them during the next class, you would understand what we were talking about.